Welcome to the online class of mathematics. In this class we deal about complex analysis and particularly we take up analytic and differentiable functions, and this particular class is going on through online mode due to the certain work at my home. So that is why this particular class is going on online. So I expect that all of you will go through all these lectures so that things become clear and I can proceed in offline lectures further. So today it is an important topic, analytic function. I will deal this one. So what are the analytic function? Last time we have taken several examples, as well as we have considered about complex functions. So what are the complex functions? So our question is, what are the complex functions? And we have taken, suppose if f is a function from a to b, and depending on the inclusion, depending on the association of a and b, we said suppose if a is a subset of r, and then two cases arises, and first case, b could be from r, b should be a subset of r, and b can be a subset of c also. Similarly, if a is a subset of c, then two cases arises, and first case is b is a subset of r, and b is a subset of c. So what we say in each cases? In the first case, because our variable, because a is a domain, so variable are coming from here, and this variable maps onto f of x under this mapping. Okay, and value are coming from b, and variables are coming from a. So because in the first case b is a subset of r, it means value is a real and variable is also real, so we say it is a real valued function, a real valued function of real variable, real valued function of real variable. And in the second one, because values f of x is coming from complex, so you say it is a complex valued function, of real variable, complex valued function of real variable. And the next one, there is certain problem. Okay, I'm removing this. Okay, the next one, and this particular thing is known as, because values are coming from r and our variables are complex, so you say it is a complex real valued function, real valued function of complex variable, real valued function of complex variable. And the next one is complex, because values are also complex, variables are also complex, so you say it is a complex valued function, complex valued function of complex variable, valued function of complex variable. We have already talked about these things and given several examples related to this. And the first one, which is a real valued function of a real variable, this particular thing will be considered in real analysis, means in we deal these functions in real analysis course. So that's why I'm not dealing this particular thing in real here. And the second one is I have already defined you. And the second one, complex valued function of complex value. This was already defined in the previous class, which is occurred offline. And in the previous class we said that any function which is a complex valued function, any function which is a complex valued function of real variable, this kind of function will appear, takes its form f of t equal to u of t plus I of vt. This is the standard form of the complex valued function of real variable. And using this particular what can say representation of f, you can define its limit, as well as suppose if t is a some point here, and t is approaching to t naught is a some point here, and t is approaching here, and if you want to take the limit, so limit t tending to t naught f of t is nothing but this is equal to limit t tending to t naught u of t plus iota limit t tending to t naught v of t. So this is the definition of limit. When function is a complex valued but of real variable. Similarly, one can define the derivative also. So what is the derivative? So suppose you are defining f dash t. What is f dash t? F dash t is nothing but u dash t plus iota times v dash t. This is the differentiation of real functions. This is also a differentiation of real functions. Real functions means real valued function of real variable. So I hope that you know the differentiation, because this kind of differentiation you have already learnt in class 12 also. So I hope that you understand this thing. And now I'm going to deal the next one. What is the next one? Let me check. Okay. So what is the next one? Next one, which is quite important, and I have already mentioned in the class that if you take this particular thing, what is the this is the important thing. It is a real valued function of complex variable. I think I have finished the last class by discussing certain things related to this real valued function of complex variable. Real valued function of complex variable. So it is a real valued function of complex variable. So now because variables are from complex, so if you take suppose it is a complex plane, and z naught is here, I have explained it earlier, and some z is approaching, certain z is approaching to this one, so then this particular z can approach this point in different ways, means by following different routes. So it is important to know here that in the case of complex, a complex number can approach to the next complex number in different ways. So that's why here it's quite difficult to find out the limit, but not impossible. It's easy. There are ways to find out, there are several easy ways to find out the differentiation or limits easily, but in general, by using the definition, it is little bit difficult to find out the limiting condition. But last time I have told you, to prove the existence is difficult than to proving non-existence. Existence prove करना ज़्यादा कठिन है than non-existence के लिए आपको कोई एक पाथ लेना है और दिखा देना है कि वहाँ पर जो है वो हाँ दिखा देना है कि वहाँ पर वो जो है लिमिट एग्जिस्ट नहीं कर रही है. इफ़ यू आर एबल टू शो दिस वन, देन थिंग्स विल be fine. Okay, in general, suppose that you are going to find out the limit of certain function. Suppose you have a function of z, complex valued function है, real valued है. तो I have given several example. One of the example is a mod z. Suppose you are taking f of z is equal to mod z. Here you can simply see that this is a complex variable. You can simply see that this is a complex variable, and whatever output you are getting, this is a real number. So obviously it is a real valued but complex variable. So there is an important thing related to this, related to differentiability of this kind of functions, and I'm going to understand that one, and after understanding that one, we will leave this kind of function because मैं इस टाइप के functions को leave करूँगा. There is a reason behind this one कि after this property, this kind of function has no more significant properties. So that's why there is no way to deal this kind of functions in our theory early after this discussion. Okay. So what can I say? So first of all, now I'm define differentiability. Now I'm defining differentiability. What is a differentiability? So continuity, you know, initially I should define continuity. Continuity means because your function is a complex function, so continuity means suppose you want to show that this function is continuous at a point z0, Suppose this function is continuous at z0. Its simple meaning is limit f of z as z approaching to z0 is equal to f of z0. Here this particular limit is nothing but it is the limit which I have defined you earlier. It means this particular z is approaching to this by different path, and you are getting, if you are getting the same thing which is equal to f of z naught, then you say that this particular function is continuous. Okay, in the similar way, we say that f is differentiable, function f is differentiable at a point, function f is differentiable at a point z naught if this particular limit z going to z naught f of z minus f of z naught upon z minus z naught exists and finite. एग्जिस्ट करने का मतलब वो फाइनाइट हो माना जाएगा, तभी एग्जिस्ट करेगा, अदरवाइज नॉन एग्जिस्ट माना जाएगा. So means a particular complex function f is differentiable at certain point if this limit exists. अब फिर से I am again emphasizing that this particular limit is nothing but it is the same one as we defined earlier. It means here again z is approaching to z naught by different पाथ्स, अलग अलग पाथ से अप्रोच कर रहा है, और अलग अलग पाथ से अप्रोच करने के बाद भी अगर इसकी वैल्यू फाइनाइट हो और यूनिक हो, फाइनाइट नहीं होगा तब भी एग्जिस्टेंस नहीं माना जाएगा. इफ इट इज नॉट फाइनाइट देन वी डोंट कंसीडर इट दैट दिस पर्टिकुलर लिमिट एग्जिस्ट, एंड इफ we don't consider the particular limit exists, and in other case if it is oscillatory, means it is finite but it is not unique, then in that case we say it is oscillatory. So for existence the value of this limit, should be finite. The value of this limit should be finite as well as unique. Now I am coming to our next point. Okay, so now I am coming at next point, and the next point says that means now I have defined differentiability. Now I am going to talk about the differentiability of what? Differentiability of real valued function of complex variable. I start this particular things by giving an example which is not differentiable. So what is the function? Suppose if you take this particular function f of z is equal to mod z. Suppose I am giving this particular thing. Is it differentiable? This is my question. Okay. So before moving further, there is another way of writing the differentiability. What is that way also? I would like to point out. So suppose in the last line I have said that f is differentiable at z naught if this particular limit z tending to z naught f of z minus f of z naught upon z minus z naught exists. I have said this one. In other word, you can say that if you take a small increment here, so if limit h going to 0 f of z naught plus h minus f of z naught upon h, this must exist. Okay, so what can we? I will use this particular. I will use this particular thing. Definition frequently. One can use both because both definitions are equivalent. There is no harm to use the first one, but second one is quite good. But here I'm again saying that this particular h is approaching to 0, but h is a complex number, so it can approach to 0 by following the different paths in the complex plane. So next we deal this particular example, and let's see whether this is differentiable or not. So there is different ways, but I will prove this particular thing using the definition. So I'm asking about its differentiability at a point z not equal to 0. मैं z not equal to 0 पर इसकी differentiability find out check करना चाहता हूँ. Check whether this particular function is differentiable at z not or not. Whether this particular function is differentiable at z not or not. So I'm putting here, let's suppose definition. So in definition I'm taking this limit h tending to 0, f of z naught is our 0, 0 plus h minus f of 0 upon h. Okay, so use the definition of f. So it gives that limit s tending to 0, and this is nothing but mod h minus f of 0 means g modulus of 0 is 0 upon h. So finally you get this is the limit of s tending to 0 mod of h upon h. Is it correct? Okay. So as I have mentioned you earlier that h is a complex number here, and which is approaching to 0 in by following different paths. So I'm taking two particular paths. Suppose I'm taking the two particular paths. Suppose this is your y-axis and this is your x-axis. Okay, this is your y-axis, this is your x-axis, and this is your 0. Okay, I'm taking the other. This is your 0. Okay, and h is somewhere. Suppose h is here and h is approaching to this thing. Suppose h is approaching to this thing along the real axis. Real axis से अगर ये follow करता है तो क्या होगा? And next we take that suppose h is here and it is approaching along the y-axis. So I'm taking these two particular paths, and once you take the first one, so in that case look at the expression. In the expression, because h is a real, so there is no need of modulus here. If h is a real, then there is no need of modulus here. You will get h only. But modulus is a positive number, so that's why you can have mod here. So suppose you are approaching this particular 0 from positive real axis. हम पॉजिटिव रियल एक्सिस से करते हैं जिससे हम बिल्कुल आसान रहे हमको चेक करना. Okay, if you follow this one by positive real axis, then there is no use of modulus here. Then you will get limit s tending to 0 h upon h, and h will become cancelled. You will get its limit 1. Okay, but in the case when h is approaching from पॉजिटिव वाई एक्सिस को अगर अप्रोच करते हुए आए, उस केस में, in that case you will have some iota something. Suppose H will contain iota something. Suppose it is iota B type, some type of things. Suppose H is equal to, because H is approaching to 0 along y axis, so the form of H will be IV, and once you put here, you will get limit S tending to 0, iota B, modulus of iota B upon iota B. So you will get V upon iota B, V cancel हो जाएगा, you will get minus I. You will get minus I. So you can imagine that when you are approaching, you can observe that when you are approaching H to 0, when H is approaching to 0, along real axis you are getting 1, but when H is approaching 0 along y axis you are getting minus I. It means it is not unique. The value of this particular limit is not unique. So that is why you say that this particular function is not differentiable. So our conclusion is what? This is not differentiable. This is not differentiable at z not equal to 0. ये z not equal to 0 पर differentiable नहीं होगा. Okay. Now I'm taking the general case. General case of what? General case of a function of real valued function of complex variable. I'm taking the general case of this particular thing, complex function. Okay. So our case is this. Here f of z, once you consider f of z, then it will be a real. जब हम f of z consider करेंगे, ये real होगा. Okay, it will be a real quantity, and z is here complex quantity. Z is here complex number. It is a complex number. So suppose that fz is differentiable at certain point. मान लीजिए कि fz is differentiable at certain point z0. मैंने माना है कि suppose that this particular function is differentiable at z0. z0 पर ये particular function differentiable है. Okay. Then what will be your conclusion? Your conclusion will be this particular limit as s tending to 0, f of z0 plus h minus f of z0 upon h is equal to this particular thing minus this particular thing upon h. This exists. This exists means it is finite, and it is finite and unique. This is finite as well as unique. ये finite होगा और unique होगा. Okay. Now I'm taking the cases. First case. Case first. When h is approaching to 0 through real axis. When h is approaches to 0 through real axis, अब h अगर 0 को अप्रोच करे रियल एक्सिस के साथ, then think over this fraction f of z plus h minus f of z naught upon h. What can you say about this? Because f is a real valued function, so it is real, this one is real, so subtraction of two real is real, so your numerator is real, your denominator is real, so ultimately you are getting a real quantity. Ultimately you are getting a real number, and if you take its limit as h tending to 0, you will again get a real number. Are you getting my point or not? This is this is most important thing. You have to understand this thing, because now I'm again repeating, because h is approaching to 0 through real axis, it means its values are real. अभी देखिए, अगर हम देखते हैं कि अगर if it is your x, it is your x axis, it is your y axis, and here is a 0. I'm denoting the 0 by another thing. Suppose it is a 0 and h is approaching to this particular thing through this line, h is approaching this particular thing through this line, then the values of h will be 0, real. So here it is real, and because you are taking the real function, so it is real, so ultimately you are getting real. Okay, now I'm moving to another case number second. What is the case second? Case second says that when h is when h is approaching to 0 through imaginary axis, imaginary axis, when h approaches to 0 through imaginary axis. Okay, in that case what will happen? In that case, again look at this particular expression, f of z naught plus h minus f of z naught upon, in that particular case our h will be of the form ib. In that case h will be a particular form ib, where I is a iota, whatever you know, ib, so it can be taken as a 1 upon I and f of z naught plus h minus f of z naught upon b, and you can take limit inside because it is a constant, so limit can be taken inside. So here b is going to 0, and in place of h you can put ib, because here you have put ib, so here you can also put, and b is approaching to 0, because h was approaching to 0, so in that case b will be approach to 0. So now consider this case. Sorry. So some lines are automatically come into the picture, so I'm removing and taking the next one. Okay, so I'm saying that here b is tending to 0 and it is the b, and here is the iota. So because f is a real valued function, so it is real, and because h is written as a ib form and b is a real, here also it is real, so whatever output you will get, that will be a real. Okay, that will be a real. Or if you write it, you will get iota times some another real. So a real number, and you are saying that the above one, this particular, and you are saying that this particular thing is this particular limit exists, it means it has to be finite as well as it has to be unique. सो एक रियल नंबर, अब हम कह रहे हैं कि एक रियल नंबर, पहले केस में रियल नंबर आ रहा था एंड सेकेंड केस में वी आर गेटिंग द कॉम्प्लेक्स नंबर. सो यू आर सेइंग दैट this real number is equal to this complex number, and this is only possible when this real number when this real number is equal to 0, क्योंकि 0 is a real number as well as complex number. So there is only one choice which is left here, it is a 0. It means that this particular limit is nothing but it has to be 0. So it is an important result which I have proved here. I have proved that if you have a real valued function of complex variable, if you have proved if you have a real valued function of complex variable, then if it is differentiable at certain point, then its differentiation cannot be other than 0. 0 के अलावा कोई दूसरा differentiation possible नहीं है. So that is why, because this particular thing is applicable in several places, it will come into the picture in complex analysis. I am not violating this one, because I have earlier said that after discussing this particular property, I am not going to deal this one. There was a reason, because now it has a limited applications. Except this, now it has limited application. So whenever we require, I will use this kind of functions, but usually we take complex valued function of real variable or complex valued function of a complex variable in whole our discussion. In coming discussion also I will treat that. So now we are left with these two. Functions, and what are these functions? And first one is a complex valued function. Complex valued function of real variable, which we have already defined, and we have also defined, not only defined limit but also defined differentiability. And second we deal the complex valued function of complex valued function of complex variable. Further we deal complex valued function of complex variable. Okay, so we have earlier defined out the differentiability. So differentiability, there is a important equation which are related with differentiability. That one is known as a Cauchy-Riemann equation. Name is I'm writing again it, Cauchy-Riemann equation. And in short, people call it CR equation. And this Cauchy-Riemann equation is a necessary condition for the differentiability of a function. कोई function differentiable तभी होगा if it satisfies Cauchy-Riemann equation. It means it is essential to satisfy Cauchy-Riemann equation. So this particular equation will be useful in showing the non-differentiability of certain function. Certain function is non-differentiable. If you want to show that, then this particular equation will be applicable, useful, not applicable. It is applicable everywhere, but it will be useful. So what is the Cauchy-Riemann equation? And I would like to point out that there are several forms of Cauchy-Riemann equation. First one is a first one is a Cartesian form, and second one is a polar form, and the next one is a complex form. So because I have written a particular book on this particular Cauchy-Riemann equation, and during my MPhil, so that is why I have several forms of Cauchy-Riemann equation. So I am going to give a first one is a Cartesian form. First one is a Cartesian form. Cartesian form of a Cauchy-Riemann equation. Cartesian form is, first one is a ux equal to, okay, before moving further, first of all let's see the general form of this kind of functions, because without knowing the general form of this kind of functions, it is not possible to understand the Cauchy-Riemann equation. So suppose if you are having f of z, because in that case you are taking, in that case you will take your variable is complex as well as value is complex. So its general form is u of xy plus iota times v of xy. So to have a look at it, here I am taking z is equal to x plus iota y. Whatever z you are taking, that is of the form x plus iota y. And with respect to that one, the general form of complex valued function of complex variable can be given into this form. Okay. So let me take a particular example so that clarity emerges, because examples are tool which helps for clarity purpose. Suppose if you take f of z is equal to z square. If you are taking this one, f of z is equal to z square, because z is equal to x plus iota form, so it can be written as a x plus iy whole square. So this is nothing but x square minus y square minus 2ixy. You will get this. And if you rearrange it, then you can write it x square minus y square in one bracket, and in the next one you can write plus iota minus, no, it should be plus here, 2xy. So you can compare this particular example with the general form of your function. हमने एक पर्टिकुलर एग्जाम्पल लिया और उसको उसमें z की वैल्यू पुट की, तो देखा कि एक फंक्शन हमको मिला जो कि रियल फंक्शन है x और y में. यू विल गेट अ रियल फंक्शन इन x एंड y, and you get another real function in x and y. So it is your u of x and it is your v of x. So that is why it was important to give the general form of complex valued function of complex variable. Once we provide this one, now I would like to give the Cartesian form of, Cauchy-Riemann equation, CR equation in Cartesian form, CR equation in Cartesian form. Okay, so what is the CR equation in Cartesian form? It is equal to u of x. U of x is nothing but, because u of x y, it is a real valued function, real valued function of variables x and y, and v was also a real valued function. V was also a real valued function of real variables x and y, and this particular thing denotes the partial derivative of u with respect to x. Partial derivative with respect to x equal to the partial derivative of v with respect to y, and partial derivative of u with respect to y is equal to minus of partial derivative of v with respect to x. This is a Cauchy-Riemann equation in Cartesian form, and I will show that this particular thing is a necessary condition for the differentiability of complex function, So we explain these things in next class with several examples. So next class will be of several examples. So I'm closing my lecture for today, and next we will deal in the next